Hello, everyone, and welcome. I'm excited to have you here today. We're about to dive into the fascinating world of machine learning, artificial intelligence, and more. On this first slide, you'll see the title of our presentation and the website, skllshot.com. Over the next few moments, I'll give you a quick overview of what we'll cover today, things like how these technologies are shaping the future and what skills you might need to stay ahead. So, let's get started. When we talk about artificial intelligence, or AI, we're referring to the broad science of mimicking human abilities. It's essentially about creating machines that can perform tasks we usually associate with human intelligence, like understanding language, recognizing images, or making decisions. Now, within that big umbrella, there's a specific subset called machine learning, or ML. What makes ML unique is that instead of programming rules explicitly for every task, we feed data into algorithms, and these algorithms learn patterns from that data. Think of it as teaching a machine how to learn on its own, rather than just giving it fixed instructions. This approach allows AI systems to become more adaptable and improve over time, which is a key part of what we're exploring in this presentation. So, in essence, AI is the broad science of mimicking human intelligence, and machine learning is the practical method we use to make machines learn from data, enabling them to perform complex tasks more like humans do. So let's take a closer look at the three pillars of AI that form the foundation of how machines learn and adapt. First, we have supervised learning, which is all about learning with guidance. The model is trained on labeled data, meaning it has pairs of inputs and the correct outputs. The goal here is for the model to predict future outcomes accurately, kind of like how a student learns from examples and feedback. Next, we have reinforcement learning, which is a bit different. Think of it as learning by trial and error. An agent, or a kind of decision maker, performs actions in an environment and learns from the rewards it receives. Over time, it figures out which actions lead to the best results, similar to training a pet through positive reinforcement. Finally, there's unsupervised learning. This is about discovering hidden patterns within unlabeled data. The model explores the data on its own to find structure, such as segmenting customers into different groups without any prior labels. These three pillars, supervised, reinforcement, and unsupervised learning, are central to how AI systems develop intelligence. They each serve different purposes, but together enable machines to learn from data in versatile and powerful ways. Let's start by talking about scikit-learn. It was actually developed by Meta, which is quite interesting. Researchers really love it because of its flexibility and the ability to work with dynamic computation graphs. This makes it very versatile for a wide range of machine learning tasks. Moving on to TensorFlow, it's known as the gold standard for classical machine learning algorithms in Python. What makes it stand out is that it's an end-to-end open-source platform developed by Google. That means it's great not only for developing models, but also for deploying them at scale, especially in production environments. And then there's PyTorch. It's another powerful framework, often favored for its ease of use and dynamic nature. It really shines when you're working on research prototypes or need more flexibility during development. All these tools are part of the modern framework landscape, which is evolving rapidly. They enable us to handle complex processes efficiently and are essential in today's machine learning workflows, especially when aiming for large-scale deployment and real-world applications. Let's take a closer look at the journey of AI/ML and how it has evolved over the years. Starting from the 1950s, we had the birth of artificial intelligence, with foundational concepts like the Turing test, which was designed to assess whether machines could exhibit human-like intelligence. Moving into the 1980s and 90s, we saw the rise of machine learning, with statistical methods and the technique of backpropagation becoming central to training neural networks. Fast forward to 2012, a pivotal year marked by the deep learning breakthrough with AlexNet, which significantly advanced image recognition capabilities. This era also coincided with the rise of GPU computing, enabling faster and more complex neural network training. Today, in 2023 and beyond, we're witnessing the emergence of generative AI, transformers, large language models, and agentic AI. These are systems that can operate more autonomously and creatively. Throughout this journey, we've gone from simple algorithms to sophisticated models that now can understand, generate, and even interact in human-like ways. This progression highlights the remarkable acceleration in AI development, driven by innovations in hardware, algorithms, and data availability, all shaping the future of AI. Now, let's talk about the inference step in the learning loop. Once we've trained our model, it can predict outcomes for new, unseen data. This is where the real power of machine learning comes into play, applying what we've learned to make real-world predictions. Next, we have model training. During this phase, the algorithm works to find patterns and establish mathematical relationships within the data. It's like teaching the model to recognize the connections and structures that are important for making accurate predictions. Before the model can be trained, we need to convert raw data into a form that machines can understand. This process is called feature extraction. Essentially, we're transforming images, text, or numbers into vectors, numerical representations that the model can process effectively. Finally, all of this starts with the raw input data. Whether it's images, text, or numbers, gathering this information is the foundational step. Without good quality input data, the entire learning process can be compromised. So, in summary, the learning loop takes raw data, extracts meaningful features, finds patterns through training, and finally allows the model to predict outcomes on new data. This cycle is what enables machines to learn and improve over time. Let's take a look at some of the exciting trends shaping the future of AI by 2025. First, there's the acceleration of drug discovery and material science breakthroughs. AI is helping researchers identify new compounds and materials much faster than ever before, opening up new possibilities for medicine and technology. Next, we have what's called AI in science, which refers to AI systems that truly see, hear, and understand all at once. These multimodal reasoning models can process different types of data simultaneously, making them much more effective at understanding complex environments and problems. Speaking of efficiency, there's a growing focus on running powerful AI models directly on devices like smartphones and IoT gadgets. This approach, known as Edge AI, enhances privacy and reduces latency because data doesn't need to leave the device for processing. Finally, we're moving beyond simple chatbots toward what are called agentic AI. These are action bots, essentially AI that can plan, make decisions, and execute complex workflows all on their own. This shift is about creating AI systems that can autonomously perform tasks, adapt to new situations, and ultimately act more like intelligent agents. All these trends are interconnected and will significantly impact how AI is integrated into various industries, making it more powerful, private, and autonomous by 2025. Let's talk about some of the key challenges we face when it comes to protecting sensitive user data during both training and inference. First, there's the black box problem. This refers to the difficulty in understanding why an AI system made a particular decision, which raises questions about transparency and trust. Interpretability is crucial because it helps us ensure that AI decisions are fair and explainable to users. Next, we have the issue of compute costs. Training state-of-the-art models isn't just resource-intensive, it also demands massive amounts of energy and expensive hardware. This makes it costly and sometimes impractical for many organizations to develop these advanced models. And finally, there's the challenge of bias and fairness. Models can inadvertently inherit and even amplify societal biases present in their training data. This is a serious concern because it can lead to unfair outcomes and reinforce existing inequalities. All these challenges, data privacy, interpretability, compute costs, and bias, are interconnected. Addressing them is essential to building AI systems that are not only powerful but also ethical, transparent, and accessible. When it comes to critical decisions, such as those involving medical or judicial matters, it's essential that human oversight remains a key part of the process. AI can provide valuable support, but ultimately, humans need to be involved to ensure responsible and ethical decision-making. It's also important to establish clear lines of responsibility for all AI outcomes. Everyone involved should know who is accountable if something goes wrong or if decisions need to be reviewed. Transparency here builds trust and accountability. Another crucial aspect is clear disclosure. Users should always be aware when they are interacting with AI, so there are no surprises. Transparency about AI involvement helps maintain openness and trust. All of these points tie back to the core themes of ethics and responsibility. As we integrate AI into various areas, we must prioritize responsible use, keeping human oversight front and center to ensure that AI benefits society without unintended harm. Keeping up with a rapidly changing field requires us to stay adaptable. It's important to understand the industry we're working in, whether it's finance, biotechnology, or another area, so we can apply AI effectively and appropriately. Critical thinking also plays a vital role, evaluating model outputs carefully to ensure they make sense and are useful. Having strong domain knowledge helps us interpret results and make better decisions. On the soft skills side, being familiar with tools like Python, PyTorch, TensorFlow, and understanding mathematics such as linear algebra and calculus are essential. Data engineering skills are also crucial to manage and prepare data effectively. When it comes to technical skills, these are the core capabilities we need to develop and continuously improve. Remember, staying current in this field means blending technical expertise with industry insights and soft skills. That's how we can truly keep pace with this fast-evolving landscape. Thank you for taking the time to be with us today. As we wrap up, I want to remind you that automotive manufacturing is an ever-evolving industry, where innovation and sustainability go hand in hand. It's exciting to see how these advancements are shaping the future of mobility. If you have any questions or want to explore further insights, please don't hesitate to get in touch with our team. We're here to collaborate and build a better, more sustainable future together. Once again, thank you for your attention and participation.